Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Kirk Gray.
Hey, Kirk, you have a background in some electronics in dealing with stuff, from what I understand.
Yep.
So I did get a call a couple weeks ago, and it was, we just got this field issue, and we got some boards back, and it looks like it's got flux all over the board. And one of the engineers was measuring the conductivity between two. The way it failed, the way they notice it is this function would fail, and there was these two pins, and they're blaming the flux residue of being too conductive, and that's why it's shorting out and failing.
Right.
And I said, okay, one, how do you know it's flux? Two, if you can see it and it is flux, why is it there? And it led to a whole bunch of questions they didn't know answers to, so they had to go find out stuff. But it reminded me of one of the very early days when I was at Hewlett-Packard. I got a call saying we got white powder on our boards, and we think it's causing a problem.
Yeah.
And I said, okay. So just due diligence, failure analysis. Let's send it to the lab. Let's do a chemical analysis, because it'll almost always help us figure out what it is and where it's coming from. Except 2 days later, I get a call from the chemist saying, and longtime listeners to this podcast have heard this story before, but it was squalene, Squalene, squalene.
No, I've never heard of that.
Me either. And so I looked it up, and the thing that showed up right away in a quick search was it's a extract from deep water sharks' livers, and it's used in cosmetics and hand lotions and stuff like that.
Huh.
And I'm like, what are they doing throwing shark livers around in this factory? And it's inert. It's not conductive at all. It's if you rub your finger and thumb together, it has a little bit of a oily lubricant type substance there. That is squalene. It's naturally occurring. It's all over us. So I started thinking, was it improper board handling and people are touching the boards, and a little bit of that goes there. And it was like, well, that's usually not a big problem and whatever. But to make a long story short, is this white powder on the board.
Was it cosmetic? Because you said it was non-conductive.
It's non-conductive.
And
it was
causing any electrical problem?
Well, it did. Yeah. It was also on your hands, besides in the factory. We were talking about it the other episode, is, factories that have humidity controlled so that it has less ESD. And this factory is similar to that. Their air conditioner was really drying everything out. So they offered their employees hand lotion, and pretty much expected them to use it so that their hands were conductive, so that they would dissipate ESD problems. Right. But if you get a fresh thing of hand lotion and you put your thumb in the middle of the board, it will make a thumbprint. And I said, the way to check that hypothesis is I called the factory and says, what's the ingredient list on your hand lotion? And squalene was the number one thing.
Huh.
And it's a naturally occurring lubricant, and it works great as a lotion, and it's just perfect for that application. And so I'm like, okay. But in order to get that much white powder on there, it's not the squalene itself that's causing the conductivity, but your hand also includes a bunch of chlorine and bromine and a whole bunch of other ions that are very conductive. Right. And so I said, well, it's the board handling. And so send me a video, get your camera out. Let's go watch people moving the boards around. And they're just thumbs and fingers all over them. And I thought, stop that. Stop touching the boards. And the problem went away.
Well, we sweat salt too.
Yes, and that's kind of conductive.
Yeah, it is very conductive.
Yeah. So anyway, there was this whole idea was if it is flux, which is a material used in the soldering process, in order to, I think it's called wetting the surface so that the solder will adhere to what it needs to adhere to and all that stuff.
Right. So it'll flow, flux is also a little bit corrosive, I believe.
Yep.
Some can be, and so whether it's a no clean flux where you can leave it on the board, or if it's not clean, you will eventually
wash it off, which has its own challenges too if it's not done properly. Yeah, so this was a no clean flux, and I said usually vast majority of flux formulations that once they go through the temperature of relief flow, they completely go inert. They activate, they do their chemical thing that they're supposed to be there to do, and then they get burned off essentially. They go inert. And so the flux, if done well, the soldering process, if done well, should work just fine. So is anybody checking the soldering process and what temperatures are actually running at? And is this the right match of flux and solder for your materials on your board and the soldering process and the variability of all that? Is anybody looking at that? And they're like, we got to check. But the very first part was, what process control do you have for your soldering process? And then I said, and then they had to go answer that question. But then the second part was, is it isolated to one area of the board? And she goes, why are you asking that? And I says, is it a repair, or is there a hand soldering step?
Right.
And I've seen some hand soldering stations where they basically pour flux all over the thing, and it's not going to enough temperature that it matters that it goes inert. But where they do the immediate soldering, it's perfect. But then they have all this active acid essentially laying all over the rest of the board. And this is some hand soldering processes are wildly out of control. And very often just touching a soldering iron onto your board causes problems. So avoid repair, avoid cleaning by getting your process right, avoid all these other things, but get it right the first time and control that so you don't have these problems.
Right, because reworking is always more potentially leading to latent defects than the original process if it's in control.
Oh, we studied that when I was at Hewlett Packard and the group was on, and it reduced the life of a solder joint of a product.
Right.
The reworked ICs, or the reworked, mostly it was the big ICs that were reworking because they were economical, that you didn't want to lose the IC if you didn't have to.
Right.
And it cut them in half, the lifetime. We did accelerated life testing on the solder, on thermal cycling, and it was less than half for a rework joint. Even a very well done rework joint was just not the same.
And it sounds like with the flux, they were kind of, like one flux that was completely, that when the board went through IR reflow, which meant the entire board got to reflow solder melting temperature, then all that flux was then activated, so it's neutralized by the heat.
Right.
Okay, and so then using that same flux for a localized touch up, then it's not going to physically work that way because the heat is localized and the flux flows way out from the heat because it's a liquid usually.
Yep.
And there you go. Right. There you go. You let, some of that active, whether, it might be a clean flux or no clean, you still have a contamination, and it collects. It's kind of sticky.
Usually will go like perfectly worse places.
Yeah. And it's sticky and things like that. And, might gather dust. I don't know.
Well, that was one of the arguments for cleaning no clean, is that it leaves a roughened surface, a tacky, rough surface on the board. And that's just a natural filter for contaminants in the air and picking up moisture and stuff like that, which can lead to problems.
Right.
And so it's like, who's paying attention? Well, we're not the manufacturer.
Well,
somebody's got to be paying attention to the process.
But until something fails, nobody really even has thought of these things or why these interactions can occur. It was like, oh, that's a surprise. We didn't realize, that flux used in this way would manifest itself one way, but when it's used for touch-up, it manifests itself as, not
an acid.
right.
This is the
So,
problem. Well, it's amazing to me is way back when I was at Hewlett Packard, I did one of my roles was to go to contract manufacturers and run a qualification run. And we had test boards with a range of different dummy components on it that were like a ball grid array that had a daisy chain pattern through it. So we could hook it up and measure conductivity through all the joints. And then we'd cut these things apart. We'd measure intermetallics. We did accelerated testing on them. We did contamination extractions on them. We did all kinds of cool stuff on it. But going through plant after plant after plant, you started to look for things that's just not right. And why do you, a major contract manufacturing facility, worldwide, huge corporation, not know this? And it's not the person on the floor's fault. It's the way they do it. It's the way they were trained. It's the way they were expected to handle the boards and do stuff. And,
right.
And so it became one of the engineers I was working with is, why do you look for all these things? All these different ways that the boards could cause problems. It's because it costs millions of dollars if our products don't work. And it all starts by doing it right the first time.
Right.
We can't repair this stuff and get it to work well enough. And we do a lot of repair, and don't do repair in our systems. Let's not do that.
No. It's the hidden factory, as they say,
Oh, yeah.
Where it's really not accounted for, and that cost and everything is kind of like, well, we've always done it this way or something. And anyway, yeah. So, people discover things, of course, the hard way.
Yep.
But and then again, the lessons learned about the flux and all that don't usually get transferred, and it may not be well documented about how something is found. Once it's corrected, nobody goes. But then if you are not aware, it can slip back again as the.
Oh yeah, no, definitely. I think there's 3 stages to this. Get it right.
Yeah.
One is you got to design the product and the process so that they actually work, that you can actually build it and build it consistently.
Right.
And the soldering process is no different. It's work with your contract manufacturer if you're doing electronics, or if you're doing steel stamping, or if you're doing molded, injection molding type stuff. Work with the people that do the actual design of the manufacturing process, the steps of manufacturing, to understand how your design increases or reduces the margins that they have, or increases or decreases the variability that they're going to see.
Right.
And you need to have serious engineer to engineer discussions to really get your design right so that it works with your manufacturing. That's number one. You got to do it right from the start. And me, Kirk, it's you design in reliability. You don't make it up later.
No, you first make a robust design, then you make consistent and capable manufacturing processes that can be controlled, not have a lot of variability.
Yep.
And the outside environment, you really can't. I mean, where the product ends up, it's up to the customer, and whether he follows your rules and your specifications or not, good luck.
But then the next part is, I think, I tend to lump manufacturing and engineering and design together, because you can't ignore the manufacturing process in the design.
No, in fact, we have design for manufacturing, right?
Yep.
So that you're consistent, you don't use a bunch of different screw sizes when one screw size will do fine for all your locations.
Oh, and you make connectors that are completely blind, and nobody except the smallest hand that has an extra elbow in it can reach, stuff like that.
Right.
It's just common sense when you think about it. But that's the first part. The second part, I think, is that the failure analysis process itself has to be done well. And hence my very first questions is, well, how do you know it's flux?
Right.
There's a lot of white powders that appear on boards.
Right.
Right. It's like,
well, the failure mode or the failure mode be caused by the fluxes. It makes sense. Where are the connections?
Yeah.
How do you chain these things connector that, is it conductive? Is it corrosive? Is it what? And
one of the things that gets me though is, they said, well, we put a probe across there and it has too much, it's partially conductive. So we think that's causing the problem. And I said, how do you know it's the surface flux that's causing that corrosion or causing that short? It could be dendritic growth. It could be, there's a weird failure mechanism inside circuit boards that goes down the hollow areas of the board and causes a filament
to conduct between two metal lasers.
Two different leads inside your board.
Right.
And there's a half dozen other ways that it could be a problem that is not the surface.
Right.
The hard part of failure analysis is if you pick the most obvious one, you'll be right many times.
Yes.
And be totally wrong in other cases. And we'll be chasing a phantom. Is due diligence. Get it right. If you're going to do failure analysis, do it as best as you possibly can. Get the outside labs, get the chemists, get the physicists involved, get to the science of it and really know what you're trying to solve. And 8 times out of 10, you first guess might be just dead on. It's that one where you go implement a change and it has nothing to do with the failure mechanism and you're back at it 2 weeks later or 2 months later, trying to figure it out again.
Well, that's one of my fundamental tenets of reliability engineering. If you don't know how it breaks and you don't know what's causing the failure, you can't improve it.
No, exactly. No, totally.
You can't fix it.
Yeah. And I think the third part of doing it right is pay attention is to the what's the right way to say this is pay attention to what your customers are telling you. And you've run into it, Kirk, I'm sure. And I'm sure many of our listeners is, oh, that was customer abuse. Oh, that was this. Oh, was that?
Well, right. There's certainly a big motivation to just dismiss it as it's their fault.
Yeah. Or it's our vendor's fault, or it's our supplier's fault, or it's our transportation's fault. It's somebody else's fault. Wait a second. It's your nameplate on the side of the product. It's your fault.
Exactly. That's the only one they see.
That's right. They're calling you. They didn't call the trucking company. They called you.
Right. And you got your name on it. Okay. You put the thing together. And if you put the thing together, you're responsible for the supply chains and everything else that goes along with it. So, and also, did you, am I misusing it? The question is, did I have my PC out in the rain or did I drop it 5 feet off of a truck? I don't know. So there are legitimate reasons for people actually breaking it.
So example is iPhones and phones in general, cell phones I'm thinking of, it took them, 15 years to finally figure out that water damage getting dropped in the pool or
in the toilet
or anywhere else is causing a lot of problems. And you can have a warranty that says we don't pay for that. It's your fault. Only so long. And as soon as somebody figured it out, they all figured it out.
Right.
And added it.
Now they're pretty much very water resistant.
Yep.
Nothing's waterproof, but they're very water resistant.
Yep.
And we don't have to worry about that. Same as with the front glass, which was the most common thing on cell phones to break, was the glass. So with Corning, Apple developed Gorilla Glass, and they made it super Gorilla. Yeah, exactly.
Godzilla Glass,
which is it's going to be even better. Although I guarantee you can break it.
Oh yeah.
and people will, unfortunately. But
that's part of paying attention. Is that one of the things I often tell people is that when you set a reliability goal, it's like, the customer is going to want it to last longer. They're going to want it to be less expensive and have more features. No matter what you put in your specifications, those expectations will change. And that's the fourth part of our setting requirements is they're okay now. They may be okay when we launch the product. They will not be okay by the time we launch the next product.
Right.
The expectations will continue to move and grow. And
right. I expect, phones. I don't know how much more robust phones can be, but they're right now, and I'm wondering, can I really take my camera, my phone, and do some underwater photography? I don't know. I'd be able to risk that right now. But
do it just before you're ready to buy your new phone.
Right, exactly.
Speaking as two old reliability engineers. We're not going to buy a case for it. Nah, we'll stick it underwater and take a picture.
Right. So
good luck with that. Let me know how it goes.
That's true. We won't risk that kind of thing. But I am feeling, that if I do drop it in a puddle or something, that it's not, I don't have to rush and put it in a bag of rice, which sometimes works, as a dust.
Well, it'll help, yeah. You use an hair dryer and blow the moisture deeper into the
Yeah. But then that gave, Apple had a little moisture indicator on the
power port,
the plug, and that saved them a lot of money and made an easy excuse for a lot of their failures.
Yep, and blame the customer a whole bunch of times until they couldn't get away with it anymore.
Well, hopefully competition and people, driving to make a better product and more capable product. That's usually what drives the technology improvements.
Yep.
And I love it.
So there's a bunch of different things to do, right? And with reliability, it's really think through right from the start is what is the set of stresses you're going to be facing, and what is this system going to be able to withstand it? And speaking for you, Kirk, it would be go apply those stresses, go figure out how it's going to break, and then make it more robust is a great way to go about doing it. It also extends to, though, that if you get a failure in your lab, is do the failure analysis. Understand exactly how it failed as close as you possibly can to the basic science, physics, chemistry, whatever. Let's get to the details of it.
Right.
It's hard to solve an imaginary problem.
No. Hopefully you hopefully get more than just one. I mean, once you reach a stress to find a weakness, that you can repeat that on one or two others to see how that variation is, how weak that weakness is. So you really want to be able to do that, and then also have more than just one to see that the failure mechanism is consistent, that it's not a manufacturing variation or flaw like cold solder joint or something like that. Mm-hmm. Because that can be a one-off that doesn't have anything to do with the design, as opposed to an intrinsic design weakness, okay, as opposed to a manufacturing induced defect. Yeah. That so that's the challenge when you're first troubleshooting a failure, is determine whether this was intrinsic to the design, or is this just now something in the variability of manufacturing, we talk about pinball machines, but that's one that doesn't have automatic soldering. You can't do that underneath the playfield. You have to hand solder each one of those joints, and that's an inherent risk.
Yep.
Okay.
Yep.
That you're not going to be able to move from.
Well, they could do TIG welding instead.
TIG welding.
Yeah. Just blast it with a high voltage spark and fuse the two metals together. They could do that. It's very expensive.
I guess so.
Damages everything around it, but exactly. There's always an option, Kirk. Come on.
And we always have cost constraints, Fred, in manufacturing we have to think about. I know. We'd all do gold plating on everything, Anyway.
Well, that causes its own problems, but so anyway, it's one of these topics of, you can pay me now, you can pay me later is what comes to mind when I heard this question. It's like, it's make sure you do the due diligence, it all the way through the process. And when you have problems, that counts too. And so we went over a couple of pieces of that. If you're doing all those things and you're getting a very, very low field failure rate and your customers are happy and your market share is growing, everything, you got it. The trick now is keep it alive, because it's
keep
it. Make sure people know that what you're doing now is why it's working. And that's a whole different process.
Right. And give yourself plenty of time to test, and give yourself plenty of samples, and depending on the cost of the product.
Yep.
But make sure that you have a sufficient sample, quantity, 5 to 10 or whatever, when you're doing halt, that you really are getting a good feel for the variation in those limits or the weakness that you find.
Mm-hmm.
And give yourself time, because it's an iterative process and you don't know what you're going to find. And once you find something, you'll want to do more testing. Okay. And you are going to reach a limit before you have to ship the product, but give yourself some time, and you might be able to ship it earlier and more reliably.
Yep. All kinds of good stuff. So if you're listening to this and if you've run into an odd substance on your circuit boards, how did that work for you?
Don't touch it.
Don't touch it. Yeah. It'll just cause, it's like a crime scene. You don't want to do that.
Right. Exactly.
But it's the idea of getting it right from the start is often a very hard sell in organizations. So what kind of hurdles or troubles do you run into of trying to help the organization get it right? And that would make some interesting discussions of what kind of barriers are inherent in the way we go about creating products these days that cause us to run into these problems and difficulties that then we have to pay for it later. Let us know. Head over to accendoreliability.com/go/SOR. A couple of ways to get in touch with us. Kirk and I and the other hosts of the show are available through LinkedIn and our About pages. So plenty of ways for you to get in touch, get an answer to what's on your mind, or give us a suggestion. We'd love that either way. And we'll look forward to you in the next show. Talk to you later. Thanks, Kirk.
Okay. Thank you, Fred. We'll talk to you soon.
Cheers. Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.